Hello viewers, this is Dr. D. Rajalakshmi, Associate Professor in CSE Department of RMD Engineering College. In today's session, let's discuss about causal precedence relation in distributed execution. What is distributed execution? The execution of a process consists of a sequential execution of its action. Actions are atomic and actions of a process are modeled as three types of events, namely internal events, message send events, message receive events. Let EIX denote Xth event at process Pi. For a message M, let send of M and receive of M denote its send and receive events respectively. The events at a process are linearly ordered by their order of occurrences. The send and receive events signify the flow of information between processes and establish causal dependency from the sender process to the receiver process. The evolution of distributed execution is depicted by a space-time diagram. This is the space-time diagram of a distributed execution. The horizontal line, this horizontal line is corresponding to process P1. The second horizontal line is for the process P2 and the third horizontal line is for the process P3. The horizontal line represents progress of a process. A dot indicates, we have multiple number of dots here, right? A dot indicates an event. The slant arrow, this is what is a slant arrow we have here. A slant arrow indicates a message transfer. Since we assume that an event execution is atomic, hence indivisible and instantaneous, it is justified to denote it as a dot on a process line. In the figure, for process P1, this is for P1. Okay. The second event, this is what is the second event. The second event is a message send event. The third event is an internal event. And the fourth event is a message receive event. Now let's see about the causal precedence relation. The execution of a distributed application results in a set of distributed events produced by a process. Here, process 1 is containing a sequence of events E1 to E5. Similarly, process 2 contains sequence of events from 1 to 6. Process 3 is containing 4 number of events in it. Let H is equal to UIHI denote the set of events executed in a distributed computation. Now let's define a binary relation arrow mark. This is what is the binary relation arrow mark. We are going to define on the set H. The set H contains the set of all events that are executed in the distributed computation. Okay. So let's define a binary relation on the set H as follows. And this binary relation expresses the causal dependencies between events in the distributed execution. For all event for process Pi and for all the events of process Pj, all the events are included in the set H. Okay. So, EIX, it represents X the event of the process Pi and EJY represents Yth event of the process Pj. Here, X the event of process Pi happens before Yth event of process Pj. Implies we have three conditions here. If suppose X the event of process Pi causally affect This is the binary relation we have in between x the event of pi and y the event of pj. We have a binary relation. This is what is the binary relation, and this binary relation expresses causal dependencies among the events of pi and pj. This is what is the symbol for causal dependencies among the events of the process pi. Okay, so if x the event of process pi affects the y the event of process pj, that is, here I must be equal to j. That means both the events are occurring in the same process. I is equal to j. Okay, so if I is equal to 1, here this will be ex1, and if here also it will be ey1. That means x the event of the first process p1, y the event of the first process p1. Okay, so both the events, x the event as well as y the event, both are belonging to the same process. That is, what is the meaning of this condition? I is equal to j. One more condition must be satisfied. This x must be less than y. That means the event y must be executed after the completion of the x the event, or otherwise the event x the event must happens before the execution of the y event. That is what is the meaning. If this is the case, then we can say that x the event of the ith process causally affect the y event of the ith process. Similarly, if suppose if we have x the event of ith process is sending message to y the event of jth process, then also we have a causal dependencies in between x the event of ith process and y the event of jth process. Or otherwise, for any event, for any zth event of the kth process, if we have a causal dependency in between x the event of ith process and zth event of the kth process, similarly the causal dependency we have in between zth event of the kth process and yth event of the jth process, then we can say that we have a causal dependency in between x the event of ith process and y the event of the jth process. So these three are the three conditions or three scenarios that are possible for causal dependencies. Here, the relation arrow mark is nothing but a lamp post happens before relation. For any two events, EI and EJ, if EI happens before EJ, then event EJ is directly or transitively dependent on event EI. Graphically, it can be represented. Graphically, it means that there exists a path consisting of message arrows and process line segments along increasing time in the space-time diagram that starts at EI and ends at EJ. For example, we have E11 happens before E33. From the diagram, E11 happens before E33. That is, first event of first process is happening before third event of the third process. Let's check whether this is true or not. Let's see the space-time diagram. First event of the first process is available here, and third event of the third process is available here, and we have to check from this diagram any path including the message arrow and process line segment. Any path is there in between this event, first event of the first process and third event of the third process. Let's check. See, we have a line segment from E11 and E12, and we have a message arrow in between E12 and E22. Then in between E22 and E32, we have a process line segment in increasing time, and then from E32 to E23, we have a message arrow, and from here to E33, we have a process line segment in increasing timing order. So we have a path from E11 and E33 diagrammatically. So we can say that E11 happens before E33. We have a causal dependency in between E11 and E33. E33 depends upon the execution of E11. Then the next example is, actually this relation arrow mark, it denotes flow of information in a distributed computation, EI and EJ. Actually dictates that all the information available at EI is potentially accessible at EJ. And based on this, we can say that the sixth event of the second process has the knowledge of all other events. For any two events EI and EJ, EI does not causally dependent on EJ. Does not implies causal dependency in between EI and EJ. This symbol, okay, it denotes that the fact that EJ does not directly or transitively dependent on event EI. That is, event EI does not causally affect event EJ. In this case, event EJ is not aware of the execution of EI or any event executed after EI on the same process. For example, E11 does not causally affect E33. Similarly, we have one more example. E42 does not causally affect E13. Let's see the diagram, space-time diagram. Let's take this first example. E11 does not causally affect the event E33. E11 in the sense first event in the first process. E33 in the sense third event in the third process. Let's check the diagram. Okay, so this is what is the event E11. This is the first event available in the first process. That is why we are calling it as E11. Okay, and the next process is the third. Next event is the third event in the third process. That is what is our E33. Let's check whether we have a path in between E11 and let's take E1, between E11 and E33 we have a path. So E11 causally affects the event E33. There's no doubt in that. But we take E31, this one, this event will take, okay, third event in the first process and E33. That is third event in the third process. Okay, let's check whether third event in the first process is causally affecting the third event in the third process or not. Let's check the path, okay, in the increasing timeline. Let's check any arrow, message arrow or otherwise process line segment is available in between these two events or not. Here, from here to here, from the third event to the fourth event, we have a process line segment, but we don't have a message arrow from the first process to the third process. So from E31 we cannot reach E33. We don't have any path from E31 to the E33. So E31 does not causally affects the execution of E33. We don't have the causal dependency in between E31 and E33. This is what is the example. In this case, the event EJ is not aware of the execution of EI or any event executed after EI on the same process. And we have two important rules. The first rule is for any two events EI and EJ, EI does not causally affect EJ does not implies that EJ does not causally affect EI. This is the first rule. And the second rule is for any two events EI and EJ, EJ causally affects EI causally affects EJ. It implies that EJ does not causally affects EI. These two are the rules based on the causal precedence relation. Concurrent events. For any two events EI and EJ, if EI does not causally affects EJ and EJ does not causally affects EI, then the events EI and EJ are said to be concurrent. In the execution, E11 is concurrent, E11 and E33. These two are the events, both are executing concurrently because there is no causal dependencies between both the events. E11 does not affect E33, similarly E33 does not affect E11. Similarly, we have one more example for concurrent events. E42 and E13 both are concurrent events because E42 does not causally affect E13. Similarly, E13 does not causally affect E42. We don't have concurrency between these two events. We don't have causal dependency in between these two events. Then we can say that these two events are examples for concurrent events. Actually, this concurrent events, the symbol, no, this is not transitive. That is, EI is concurrently executing with EJ and EJ and EK are concurrent events. It does not imply that EI is concurrently executing with EK. There is no concurrency in between EI and EK. EI and EK are not concurrent events. For example, E33 and E42 both are concurrent events. And E42 and E51 are concurrent events. However, E33 and E51 are not concurrent events. So, for any two events EI and EJ in a distributed execution, these are the three possibilities of the events. EI causally affects EJ or EJ causally affects EI or EI and EJ are concurrent events. Thank you guys.